All right, hey, how's it going, guys? And it's gonna get crazy today. Section 5.6, the basic proportionality theorem, your final section of chapter 5. And in case you're not convinced how crazy it's gonna get today, hey, with a diagram like this, we can deduce that the following proportions are true. Now, here we have side length O is AQ, side length L is QC, side length, this length A represents AC, H represents AB, C represents BC, and P represents PQ. And what do I notice about PQ and BC? Ooh, parallel lines, right? Parallel lines here. So I got a parallel line intersecting two sides of a triangle, right? It's parallel to the third side. Triangle APQ is going to be similar to triangle ABC by AA, right? Angle A is congruent to itself. This angle is congruent to that angle, right? Because they're both corresponding angles. And I've said enough here, guys, right? We have all these letters here. I wanted to show, instead of writing AQ and QC, that would have been completely overwhelming to have two letters for both these distances. So I'm just doing the one little letters here. This is AP right here. And without further ado, this is how crazy it's going to get today. Oh no, you're crying a little bit here. Your Thursday asynchronous class set, and you're just like, why? I needed to, kind of relax a little bit. It's Thursday. No, I'm not going to see you, Mr. Ford. But no, it's on. It's on today. So this is what this is going to be about today. Get used to this diagram, my friends, because it's going to lead to this. And all these statements, by the end of this, you're going to see that these are true. You're not going to see why AC over OB is true quite yet. But here, if we have, let's see, where is it? Even A after. Oh, A is right here. A over C is the same thing as O over B. Huh, interesting. It's true. It's true. We'll figure it out all later. See you guys on the other side.
I never knew there was a love.
All right, Mr. Ford. Wow. My brain is already spent from looking at that opening slide. So what that opening slide was all about, we're going to have a diagram. We can set up a lot of proportions that we know are true, right? Theorems are facts, right? We want to be able to introduce and use and manipulate as many facts as we can, right? That's our goal as humans, to establish facts and manipulate it. So anyways, let me pull it back a little bit here. Let me pull it back because this is really the diagram that we're going to be working with today, our last section. Okay, we're only doing half of the section too, believe it or not here, but half of your section has to do with something called the basic proportionality theorem, or triangle proportionality theorem, as your book calls it. I like the basic proportionality theorem better. I'll get to that in a little bit. Okay, what we have in front of us is a triangle, okay, right? You notice here we got triangle RST, and we have a line that intersects two of the sides that's parallel to the third side. Didn't mark parallel there? I could have marked that parallel here. Anyways, you might be wondering what the heck this is all about here. You believe it or not, I was actually in a geometry biker gang last year with I had a ninth grade geometry class, just one geometry class. It was pretty good. But we became the Hells Angles. That's right, the Hells Angles biker gang geometry club. And believe it or not, before winter break, that's right, we got to this before winter break, okay? I made this suggestion to my gang. I was like the head of the gang. Right? Pretty sweet stuff. Ahead of this motorcycle gang here. So what I said is, you know what? If you're a motorcycle gang, you get all tatted up, right? So this is what they all did, right? Just ask if you have friends who did this, took this geometry, were crazy enough to take it with me last year, right? Because I'm a crazy person. They have this diagram. If they don't, they're out of the gang. They're out of the Hells Angles. So anyways, suggestion, you want to join the gang too, don't you? Yes, that's right. Get this diagram tattooed to your body. Well, it's already afterward. Right? Just get it tattooed now. Sometime before spring break, get it tattooed. Because believe it or not, what do I mean by that? This diagram is going to come up a lot here, okay? So when I have a line that intersects two sides of a triangle parallel to the third side, there are a whole bunch of crazy proportions we're going to be able to set up. First of all, if this is A and this is B, then I go small to long is going to be the same as small to long. Okay, small to long. Small to long, same as small to long, because these are similar triangles here, right? T is congruent to itself, right? That angle congruent to this angle right here. AA, right? AA. You can even grab these ones here. Why are those angles congruent here? Well, this is parallel lines cut by not cut by a transversal. What am I talking about here? Yeah, parallel lines cut by a transversal here. Corresponding angles congruent. Corresponding angles congruent. Okay, so we know that A to B is going to be correct, and B is the whole side, right? That's RT. We're going to figure out right? A whole bunch of other proportions, we can set up that we know would also be true, okay? Also be true. And that's what this next slide is about here before we actually get to the basic proportionality theorem. Let's go ahead and jump on to the next slide. Go away. Yes, and we get into something called proportional lengths. Put this in your notes. We got a definition today. Okay, definition. And this definition, like a lot of definitions you have in the book so far, can be kind of confusing at surface level. So you want to spend the time, the next like 20 seconds to write it out. I'm going to do fast for you. Okay, write this out here. This first definition of today is divided proportionally. Okay, a point, 2 points, right? It will require 2 points. 2 points can divide 2 segments proportionally. What does that mean? Well, I know that like 2 points, every segment has a midpoint, right? So if I have a midpoint on one and a midpoint on the other, right, then I got like a 1-to-1 ratio going on in one segment and a 1-to-1 ratio on another segment. So this divided proportionally thing, these points that are being described here aren't necessarily midpoints. These are just points that, well, if we look at segments AB right here, okay, so it says segments AB and segments CD are divided proportionally by points L and M if and only if. Okay, I'm just showing you one right here. A point, so we're talking about a point. Okay, if a point on a line, right, on a line segment, okay, they're all collinear here. This point here, L, divides segments AB, and it's not necessarily a midpoint, right? L is not a midpoint. So L just divides segments AB into, I don't know, right? This might be like 3x, this might be like 5x, right? A 3-to-5 ratio, right? 3's here and 5's here, okay? 5's here. So L divides it into a certain ratio. This other segment here, M, if it divides this segment CD into the same ratio as L divides segment AB into, then we would say that those 2 points divide the 2 segments proportionally. Okay, pretty confusing. Maybe draw the diagram out, then we can talk a little bit more about what this statement up here is saying, but maybe we'll digest this. Copy it out. Give me a second. Okay, ready, set, go. Copy. All right, ready? Ready to talk more? Do I need to go to the next slide? No, I don't go to the next slide. Then. Okay, so let's maybe talk about it here. Okay, so this here, right? We notice here L is here, M is here, okay? This here, L is collinear with A and B. M is collinear with C and D, right? So L is a point on segment AB that creates 2 segments. So if you're a point on a given segment, you're going to create 2 segments here. And AL to LB is going to be the same ratio as with point M right here. Here, CM to MD, right? So here we have the M's in here as well here, okay? So if this is 3 and this is 5, for instance, okay? And this is 6 and this is 10, for instance, right? It's a specific ratio, right? Specific ratio across here. We would say that L and M are dividing those segments in the same kind of ratio as one, the same proportion, right? Same proportion here. Because 3 to 5 would be the same as 6 to 10, okay? It's a little confusing, but let's look at it in terms of a different diagram here, which is going to involve a triangle, right? Because we have a parallel line going into a triangle, like similar to how we saw earlier, right? We have a parallel line, okay, right here. The reason why I want to talk about this here is that segments PQ would divide, right, as I said a second ago, would divide segment TR and TS proportionally here, meaning TP over PR is going to equal TQ over QX. That's what dividing proportionally means, right? It means it'll set up a common ratio between the existing segments that we have here, okay? So a little bit confusing, but maybe we need to see it within the context of a triangle, okay? That's going to be the next thing in a second here. Okay, oh, wait a second. Let's think about this a little bit more, because this definition here, divided proportionally, means that point is going to set it up so this part to this part, right, would be in the same ratio as this part of the whole segment to that part of the whole segment here, okay? That's the way you literally read this, dividing proportionally. That point creates this over that is the same as that over that. There's an extension of this that I'm going to tell you about now, which kind of connects to what you saw at the beginning in all those proportions, which is this, boom, we got a whole bunch of other stuff that we can say, make me a little bit smaller here. We got a whole bunch of other stuff that we are actually allowed to say here. In addition to that original AL to LB equals CM to MD. That's sort of the idea of L and M dividing AB and CD proportionally is AL over LB equals CM to MD. But as we know with proportions, we can manipulate them and say different things, right? Set up equivalent proportions, ones that we know are true, because proportions have all these properties to them that can be derived by multiplication property of equality and addition property of equality if you're the denominator add, right? You're adding a 1 to both sides here. So anyways, we can actually make more conclusions about these particular shapes here. And that's all listed down here. So it can help to get your head wrapped around this a little bit here first about dividing proportionally. What's something I can say? Well, the definition of dividing proportionally means that L and M are going to create AL to LB in the same ratio, right? Which means equals CM to MD here. But beyond that, there are some other things we can say that can easily be derived starting with this, okay? First of all, if we knew that L and M divided segment AB and segment CD proportionally, we could also say this up here. And let's see if we can maybe come up with a justification of this. And I'll go ahead and flip on the pen. So what do we have here? AL all of a sudden would go to CM, which is right here. LB goes to MD, which is right here. So this is a little bit differently here, okay? So L and M divide this proportionally. AL to LB equals CM to MD. But one thing kind of neat here is this is small to large in the smaller segments equals small to large in the larger segments. Here, what statement's being made here is that the small in the small segments to the small and the large segments also going to be in proportion with the large and the small segments to the large and the large segments. The large part that is here too, okay? So this is actually a true statement as well. That's kind of neat, right? That's kind of neat here. If I knew AL equaled LB, CM equaled MD, right? We're divided proportionally. I also know that that's going to be in a ratio, and that's going to be a ratio together right here, okay? How would we prove that? Wait a second. This is dividing proportionally. This to that is this to that. How do things change? What do we notice here? Oh, I noticed it here. Look at this. AL is still in the numerator, MD is in the denominator. My extremes haven't changed, but what has changed? Okay, look at this here. They choose places. This is CM up here. That's LB down here. So through a mean swap, okay, that kind of proves if I divide proportionally, yeah, this smaller part to this smaller part, same ratio as as we go from the smaller segment. It's larger part to the larger segment. It's the large part here, okay? And, that's another conclusion you can make if it divides proportionally, okay? Check out a few more here. What about this one here? What's going to justify me? So now, instead of this, right, small to larger equals small to larger, if indeed L and M are placed in such a way where they're dividing segments proportionally, now I can say large to small equals large to small, right? MD over CM for that other ratio here, okay? What can I justify that? Yeah, I mean, I just flipped it. Look, check it out here. This is AL over LB. This is LB over AL. Well, here, this is invert the fraction. Okay, so it doesn't really matter. Okay, part to part this way is going to equal part to part that way if it's indeed divided proportionally. If this is a 3 to 5 ratio, and that's at a 6 to 10 ratio, then 10 to 6 ratio is going to be the same as 5 to 3 ratio, right? They are. 10 over 6 is the same as 5 over 3. Okay. What else can we deduce? We can deduce another thing, make another conclusion about actually wholes to parts here. We haven't talked about those yet. So this is another property of proportions that might get us to this one, for instance. Who the heck is calling me? 415 number. Hopefully it wasn't one of your parents. But anyways, let's check this one out here. How can I justify this? Okay, how can I justify this one right here? I don't know if I can justify this one yet. So maybe go to that one later because I haven't even talked about CD. Have I? Have I talked about CD? Okay, well, CD's up here. Maybe we'll talk about this one here first. I think these connect up together. Check it out. How did mine change? Okay, inverted the fraction. The original one, inverted fraction. I get this one. How did it change to get to this? How did it change? Let's check this one out here. Okay, so here, this one on the left side here. That's part to part equals part to part. This one here is actually the whole segment. Okay, what I call this is the whole. Okay, this is a whole, and this is a part. You'll hear me say that. Okay, I've been saying that a lot this year using segment addition postulate and angle addition postulate. But here we're setting up ratios involving parts and eventually into wholes. Okay, part to part equals part to part. But here, this is a whole here, which is length AB, and this is a whole here, which is length CD, which we have up top here, okay? So I knew that part to part equals part to part, but now I have whole over part equals whole over part, and I have the same denominators here. How did I get there? Well, what did I do? I think that somebody just said it out loud, actually, okay? Is that we took the part that was in the denominator, right? Remember, we have a property of proportions that says we can add the denominator to the numerator, and we know we would have a true proportion here. So check it out here. LB is in the numerator, right? That's a part here, right here. But I have AL in the denominator down here. So what I can do to get from this to that over here is that I can have my part here that was earning the numerator, add what was in the denominator, right? What was in the denominator? AL. That was the other part, okay? Plus AL. And, you know, I added that here. Look, same denominator. It's like adding 1 to the left side. I'm going to add 1 to the right side of this, which is I'm going to add the CM, right? CM over CM would be 1. So I know my equality is maintained, okay? How does that connect to this over here? Well, by the segment addition postulate, right? All of a sudden, our numerator is LB plus AL. And what is LB plus AL? LB plus AL equals AB. Part plus part equals whole by the segment addition postulate. And what is MD plus CM? Okay, MD plus CM equals CD by the segment addition postulate. So there's my CD, there's my AM, and this is true. Key way to get there was the denominator add. Okay, denominator add. All right, let's keep jamming, guys. Just get settled in here. You got a lesson today. I can try to give you this lesson here. It's just lots of proportions we got to realize, hey, those are equivalent. What to look out for. Okay, so maybe we'll look at the other ones kind of quickly here. AB, so this is part to whole. So this is really getting messy, this diagram here. Whole. AB to LB is going to be the same as CD, that whole, to MD. Okay, so whole to right part equals whole to right part right there. Okay, right there. So how could I get there? How could I prove it? Well, earlier, I had here in the denominator, I had LB and I had MD. So that's how those connected, was through the same logic that I had. I'm trying to move this on for you guys here, but I wanted to change colors so maybe you can see it a little bit more closely. This here, denominator add, would justify that statement here, okay? So what am I showing this to you guys like this? Any kind of ratio that kind of visually makes sense in this situation is going to be true, right? The whole, okay, the whole here to, we're talking about this one right here, to this part is going to be equal to the whole to this part right here. If indeed that point is located in such a way as it divides that segment partially, right? Partially, okay? AB over CD, whole to, oh, no, this is part to whole. We can go part to whole, right? We can just take the reciprocals of these, okay? And, yeah, do we take the reciprocals? Yeah, it looks like reciprocals here. AB over CD is true. So AB is the whole over the part. Oh, wait, part. Oh, actually, here, this is a little bit more difficult here, too, as well. We can say whole to whole. Okay, this one here, whole to whole, which is AB over CD, is the same as this part here, right? LB over MD, right? That part here. So corresponding parts, right, will be in the common ratio here. So meaning the whole to this whole here equals this part to that part there. And I'm even losing track on how I would justify this, to be honest, right here. So how would I get to this here? AB over CD equals LB over MD. You know, denominator. Oh, look at that. We can flip these means. Okay, so this one gets to this one through a mean swap. Okay, through a mean swap. So this is pretty crazy. There's just like so many connections you make here to justify this. So that means whole to whole equals this part to that part. Okay, whole bunch of stuff here. AB is the whole again, and this is the whole. So that means what we're talking about here is the left parts, right? Left parts down here. Okay, of course you can flip any of these. You can flip it. You can invert stuff to make them all true to one another as well here. Okay, so this one connects to this, I think, with a mean swap as well. Mean swap. And we're good to go. Okay, so don't write all those down. Like, you're never going to memorize this here, but just know dividing proportionally can let you set up a whole bunch of freaking proportions, okay? They could be like this one here, which is a part to part. Okay, take away this. The proportions, when you're dividing proportionally, could either be part to part, or they could be whole to part, or part to whole, right? Or part to whole, okay? And it could be mixed up, right? Going on different ones. But you'll see some things that are not actually kind of logical, that won't be true, okay? But as long as you logic through it, your proportion is probably correct. Okay, without further ado, let's get to it. Finally, talking tattoo time. Get this down. Get this. Drop. Making sure they're parallel too, right? Make sure they're parallel to here too, or else you're out of the hell's angles, my friends. That's right, you're out of that. It's the coolest gang ever, right? Motorcycle gang here. Anyways, check it out. All right, you're putting this in your notes here. You got basic proportionality theorem. Your book is going to call this the triangle proportionality theorem. And I like basic proportionality theorem better because I'm pretty basic. But more importantly, the white textbook, which is a lot of freshman classes have, call it the basic proportionality theorem, and I like that better as a name. It just flows. It just sounds better. Okay, you got enough triangle theorems. That's with the word triangle inequality theorem, right? Triangle. I don't know. Triangle midsegment theorem, you're going to have the triangle angle bisector theorem coming up this section, which will be the next lesson. Look forward to that. So anyways, I don't call this the triangle proportionality theorem. I call this the basic proportionality theorem because it's a very basic way of setting up a whole bunch of proportions, okay? And that is if a line parallel to one side of a triangle intersects the two other sides, there's just two, not other two sides, I guess, other two sides, parallel to RS, is where PQ is, and P and Q are both on TR and TS. So anyways, if a line parallel to one side of a triangle intersects the other two sides, then it divides those sides proportionally, right? Which we've been talking about a little bit here. But let's see if you can actually get like the legitimately here. We'll talk about the proof in a second. You read the proof in the book. Well, that's actually what we're going to do in a second. I'm going to have you read the proof. We'll pause for a minute. You'll read the proof, and then we'll just fill in some of the answers together. So you'll actually see, yes, this is a fact. But check it out here, right? If I have PQ parallel to RS, then in this triangle here, then the two sides that got intersected by that parallel line divided proportionally. So question, if, right, the consequence of a statement here, right? This is an if-then statement. The if is the premise, right? That's our given, right? PQ is parallel to segment RS. The then establishes what we need to prove in this here, okay? So the question is specifically with this diagram, in order to prove this theorem, what do I need to prove? Okay, well, the two sides need to be divided proportionally. What does that mean? The proportion, what's my proportion going to be? Well, it really could have been any of these proportions that were on this last one, right? That will get us there. But what's the basic definition of divided proportionally? What do you think here, right? P and Q, so P divides TR and Q divides ST in such a way that they're divided proportionally. What does that mean? Well, it just means that PR over PT is going to equal QS over QT. I hope you said that here because that's what I got here. Or it doesn't matter the order you put the letters in here because RP, PT, that's the same thing as PR and PT. Anyways, SQ and QT. So anyways, I think you got the idea here. This shorter segment of the whole thing here over this larger segment of the whole thing here. So part to part equals part to part in this situation. As long as we can prove that, right, we're going to know a whole bunch of other proportions are going to fall from this. We'll get to that later. My friends here, okay? Without further ado, we got this set aside here. The next step of this is for you to actually pause this video, pause your lesson for a little bit. Proof is on page 233. And read through it now and prepare to share your reasons. See if you can crack the code of this. Like, seriously. Open up the book and read it. Ready, set, go. All right, give me my find this for you. Let's find it for you. All right. There you go. I'll leave this up here for a second. Take like 30 seconds and see if you can crack the code. How does this proof work? We'll go over in a second. Ready, set, go. Look at this. I'll give you 2 minutes. Go. We're almost done. We're almost out of time. Statements and reasons, guys. Back with me. All right, let's talk through these. The more you do the proofs with your teacher, right, the better you'll pick it up. More confident you'll be when you're out there on your own. So let's at least give it a shot, right? Maybe you got stuck somewhere. Maybe we can get you through it, and you'll be stronger, better off here. All right, let's take it away. Who's got my first reason here? Thank you for jumping on here. Given premise. PQ, segment PQ is parallel to the third side. And it's going to divide it proportionally, right? That's going to be the consequence. We need to get a chain of reasoning to show that it does actually divide it proportionally, right? PR over PT equals QS over QT, dividing proportionally. Those 2 points, R and Q, are divided those proportionally. Anyways, angle 1 is congruent to angle 2, angle 3 is congruent to angle 4. How do I know that? Well, I have parallel lines. They're cut by a transversal there, another transversal there. So no, 1 and 2 are congruent, 3 and 4 are congruent because they are corresponding angles. So if 2 parallel lines are cut by a transversal, then the corresponding angles will be congruent. And those are the conditions that are required for corresponding angles to be congruent. Next up, what's that? Oh, my friends, I think you got it right away. Thank you. It's the AA postulate. Okay, so once I have angle 1 congruent to angle 2, angle 3 congruent to angle 4, then TPQ is similar to TRS, AA similarity postulate. Okay. Next thing they say here, I would just say definition of similarity. As soon as you get, it's similar to like when you get triangles congruent, as we did in chapters 3 and 4, the next step was CPCTC to say that corresponding parts of the congruent triangles were also congruent. Here, you're not trying to say corresponding parts are congruent because they're not, right? RT is larger than PT. So you're trying to say that the ratios are in proportion, okay? So I would just say definition of similarity. Once you have things proved similar, definition of similarity is going to be your next thing. And we want to say RT, okay, RT to PT is the same as ST to QT, okay, to QT. So they're going large to small, large to small. Usually they go small to large, just neat, right? Just whatever it gives you more answer. Okay, so you can say definition of similarity. But you can also say this, corresponding, not CPCTC, CSSTP, right? CCSTP, I think that's it. So CSSTP, I think that's it. Corresponding sides of similar triangles are in proportion, right? In proportion, not congruent, but in proportion, okay? So we have that there. What's the next step? Well, this, right? We don't care about RT over PT, right? We care about PT and QT in the denominator. Actually, that's why they chose it like that. Large to small equals large to small because, right, this is what we got to prove. We want to prove whole to small equals whole to small, right? Actually, part to part. My bad. Large is the whole. So whole to, they're both wholes, I guess. I'm saying too much here. We basically just want to replace RT with RP. How do we get there? RT is the whole of the segment. ST is the whole of the segments, but I want to get RP here. And QS, what helps us get there? How do we get that all in one statement? That's the segment addition postulate. That's right. I'm not going to say much more about that. I know it's still confusing for you people, but I won't say much more. Okay. So now I can write this, okay? I also know this here. This is going to connect to step 4 actually here. And what's my justification for that? Well, this looks like it's just, well, never mind. Actually, it doesn't connect to step 4. It connects to step 4 a little bit. I guess it's substitution, okay? So I'm substituting RP plus PT because it equals RT by the substitution postulate. I can replace this with RP plus PT. SQ plus QT, I can replace this ST thing here with what it's equal to, which is SQ plus QT. So that's going to be substitution. Step 5 into 4, okay? Last thing is going to be property of proportions. It's kind of the reverse, right? Kind of the reverse. We haven't done the reverse. Kind of the reverse of the denominator at, okay? Technically, if I took away 1 from both sides of this, if I subtracted 1 from this left side here, subtracted 1 from this left side here, I could cancel out the QT over QT, right? QT over QT just equals 1. PT over PT just equals 1. So if I want to get rid of those, that PT there and that QT there, I would just subtract 1 from both sides, okay? But it's just kind of the reverse of that property proportion, the denominator add thing, okay? And then that's what's going to get you to what you need to prove, which is that this action here is divided proportionally here. RP to PT equals SQ to QT. And because you got there through this chain of reasoning, or the book helps you as well here too, you've proven it. The basic proportionality theorem, okay? You with me? Because, that's a pretty important one here, okay? It's written out like this. When we have that parallel line going through the triangles, we can immediately deduce this. That to that equals that to that. We don't need to prove triangles are congruent because we already did that in the proof of this theorem, okay? So part to part equals part to part, but hey, there's a whole bunch more we can say. Let's do it. Shall we? More we can say here. So, of course, we're not just limited to that statement here. Okay, why? Because we know we can manipulate this proportion to make other statements about other ratios that we would know would have to equal each other. And the more you know, the better off the world is, right? That's it. That's it here. Again, this is not going to impact your day-to-day life, but it's going to help society if more people just learn how to learn things. Okay, that's what you're doing this year. You're learning how to learn things. One of the main things this year and also in college, just learn how to learn here. So let's check this one out here. Okay, we're not limited to RP to PT equals SQ to QT because we, for instance, in the previous proof, we already knew that RT to TP equaled ST to QT, right? That was in there here too. So if we use basic proportionality theorem, you could say part to part equals part to part, but you can also say whole to part equals whole to part, okay? In fact, you can say 6 things. There are 6 things total. So here's maybe where you put it down and just try to follow the logic along with it here, okay? So 6 proportions can be said as a consequence of this situation where we have PQ parallel to RS in a triangle. Then we can say 6 different proportions and their inverses, so 12 total. So let's go through them all here right now. Okay, so let's check this one out here. Basic proportionality theorem, well, that's just part to part equals part to part. So this is similar to what we have up top here. This is the bottom. It's kind of the inverse. Part to part equals part to part, okay? We're allowed to say that. We're also allowed to say this just by reason of basic proportionality theorem. Your book calls it the triangle proportionality theorem. But anyways, this is also part to whole equals part to whole. Okay, why again are we allowed to say that? Well, we're allowed to say A to B is the same as C to D, basic proportionality theorem. And A, if we added B, well, let's see here. We're going to get B, B to A. So here it is. B to A equals D to C, right? Part to part. Add the denominators. I'd get B plus A over A equals D plus C over A, and D plus C is just K. B plus A is just J. So we can say J over A is the same as K over C. There we go. Whole to part equals whole to part. We can also say part to whole equals part to whole. We can say that. We can say a whole bunch of other crazy things here. Okay, this one's going to connect to that one, it looks like here, because our means just swapped here. And what does that tell us here? Right? You just got to focus so hard, man. Asynchronous classes, nuts. Okay, the means moved here, but what does this tell us? This part of the left side here to this part of the right side here, going to be in the same ratio as that whole of the left side to that whole of the right side here. There's so many proportions you can say involving a tattooed diagram like this here. Part to part equals whole to whole. Okay, we can roll with that if you want. A to C, so here, part to part. We can also say part to part over here equals C, equals part to part equals, and then B over D, part to part over here. We can say that. We can say so many things, okay? We can even say these things here too. Lower part to, so left bottom to whole left equals right bottom to whole right. Works out, right? Totally works out here too. And finally, B over D, okay? B over D, left bottom to right bottom equals left top to right top here. I don't know if I really fully justified it. I guess I did because this was just a mean swap of an earlier one. Everything's connected, right? Everything's connected here. So if we do mean swaps, all of a sudden we're talking about left side versus right side versus like, lefts together and rights together, right? We can actually go this to that equals this to that, okay? Or these two together equals those two together. Or this to, I don't think we can say that to that equals that to that. Can we? Yeah, we can. So there's a whole bunch of stuff we can say. Anyways, you'll get practice with it here. All right, real quick here, because you're probably zoning out. You're like, this is too